much more complicated equation, you have one simple equation if you do it relativistically invariant.
Great. I love simplifying things.
Yeah, that's always the goal of physics, to make it as simple, to make our understanding as simple as possible.
So I'd like to review it again.
Yeah, and there's also the far velocity,
Right.
u mu.
I believe we covered that in a past session.
Yeah, that is dx mu ds. And ds is invariant distance.
The space-time interval, right?
Yeah. So you can make only one invariant out of these two. That is a mu u mu.
Why is that?
Because that's all we have. You could, it should be in some sense dimensionally correct. Maybe you could argue you could also make d mu x mu if you have a particle. So you want to have an interaction of a field that is a mu. This is really the field, the electromagnetic field, with the velocity. So what can you write down? And experiment in the end will decide which one is correct. You could write down the square of this. That is also invariant. So there are a number of possibilities.
Oh, right. So there was only one invariant product dependent on these two, and that would be a mu u mu.
The only one that the correct one is this one.
Right.
So you know what are the possibilities dictated by invariance, and there's only a very small number of possibilities. For example, a0 squared minus a1 squared can never be a correct interaction term, or a0 u1 cannot be correct. That is not invariant. So you know what kind of interaction gives the right physics. And that is why it is important to know that. And it is really also important to understand the whole concept of this field, that they are related, they are not independent components.
What is for potential anyway? What is it a generalization of from classical mechanics?
So you know the potential is a battery like this. You probably don't know this kind of battery anymore. That looks like that. And there's 4.5 volts. Okay. That's a potential. There's a potential difference.
Right, potential difference. Sorry, I'm used to it being called voltage because I don't study electricity and magnitude that much.
Yeah, and
right.
So that's one potential, and this is really the potential involved, say, and that is if you have a charge. A charge has a potential E over R, where this is the charge, then this is the potential, and if you have another charge, they interact with the Coulomb's law. And this is the potential energy for the Coulomb. But this is only the static potential. That would be A0. A0, maybe is equal to phi.
Right, so this is not for moving charges?
And this is, this actually can depend on time. So also moving, when the charges are moving, this potential depends on time. But there are also magnetic fields. Magnetic fields are always written as B. And that are actually quite different forces, at least apparently. And what we know is for magnetic field is that the divergence of a magnetic field is equal to 0. You know that?
Right.
And because this is the case, it follows that the magnetic field can be written as the curl of a vector potential.
Right.
This is called a vector potential. Do you understand that the divergence of this is 0? You understand this? This is equal to 0. This is static
right.
always.
What is D? Or
this is the gradient operator.
Oh,
that is
sorry.
dx, dy,
Okay.
dz.
Great. So
Do you understand that this is 0?
I'd like to see a little bit of justification.
Yeah. So if you have the exterior product, so you have two vectors, A and B. The exterior product is a vector that components, you can represent the magnetic field in only two components because you have this freedom. And this is called the gauge freedom. And many of the most important theories in physics are all gauge theories. So this is a very important concept. So from a theoretical point of view, you like this construction.
So essentially, for B is equal to the curl of A can be added to any gradient of any 3D function, and it can just stay the same.
No, this can be added to any A.
Right.
So
does lambda have to have any special properties, or is it just a general function?
Gamma can basically be anything a priori. In quantum theory, there can be constraints. Okay. But a priori, it is really undetermined, and but it may have some constraints in the end, depending on the case you're looking at. So that's one reason to have a potential. The same reason as when you have an electric field, you have electric field. Electric field is the gradient minus the gradient of the potential. In this case, instead of having three variables, this is a vector, you express it in terms of one variable. And that's a big gain.
Why is that?
This is only one. So what you have that the curl, if there's no time dependence, so this when it is static, then the curl of E is equal to 0. Okay. And then you can solve this equation by putting E is equal to minus the gradient of phi. And again, you have the exterior product of two the same vectors, and that's 0.
So wouldn't that mean that? Okay, never mind.
So that is, so that's really the motivation. The motivation is to introduce potentials. It simplifies life. It is simpler to solve the equations. The equations of electromagnetism are the Maxwell's equations. The goal of Maxwell theory is to solve those equations. And they have many solutions. And they are important. You might want to know, why do we see that light? Why is the sky blue? And well, why can you actually receive internet over a cable, a fiber optics cable? Why does the signal not get lost? Fiber optics cables, they are very long, maybe 100 or 1,000 kilometers. We can receive fiber optic signals from Europe via underground cables, not underground, underwater. So these are all the things you want to understand from electrodynamics. Also, how do electric cars work? Electricity is everywhere in our society. Like this microphone is also electric. Almost everything in modern society is determined by the electromagnetic force. And we want to understand that.
And that's how we have a lot of the technology we have today, because we're able to predict how electromagnetic forces interact with the world around it.
Yeah, we know that, and from a physics point, we are not engineers as physicists. We always like to understand the foundations. And that is why we try to formulate the theory as simple as we possibly can.
I see.
By looking at the foundations. And that is one reason we want to introduce a potential.
So essentially, we're trying to get everything from classical mechanics into an invariant form.
That's right. You want to have the basic building blocks of any theories should be based on relativistic invariance. And so this is relativistically invariant. That's why we are doing that.
Right. So given the value of for velocity, we're trying to find some for potential for which that is invariant.
Yeah. So then the question is, what is the correct for potential?
Right.
And the starting point is the continuity equation. And that is that the divergence of the current density plus 1 over c d rho dt is equal to 0. This is the current density, and this is the charge density, the density of the charges.
I see.
And do you see why this equation is valid?
No, not really.
No. To do that, you integrate, you have some volume here, some volume here. So the current can flow inside the volume, that is J. And what we are going to do is we are going to integrate this over the volume, and also 1 over c, and also integrate d rho dt over the volume. And now we can take out this derivative. It is ddt of rho dv, and we integrate it over the volume. So what this is the charge inside the volume.
Right, because it's the charge density times the volume, so it has to be the charge.
And with the derivative is the change of the charge density.
Is that?
And for this, we write this as integral j dot n times dA. This integral is equal to a surface integral. And there's a theorem. It is a Gauss theorem. You can accept that.
Sure.
And the interpretation is that the n vector is this vector, is perpendicular to the surface. Mm-hmm. And if the current is in the n direction, it is on the outside. If the current goes in the n direction, this is the amount of charge that flows out of the surface. And if charge flows out of the surface, then this thing is negative. So because if I bring this to the other side, you get a minus sign. So that means the charge flowing out of the surface is equal to the charge that is inside the volume. So this equation really tells you that a charge is conserved. So the charge that flows out of the volume you have, it can be any volume, it could also be a cube, like this, is equal, the charge that flows outside of the cube, out of the cube, is equal to the change of charge in the cube.
So this equation is birthed out of the fact that charge is conserved, or vice versa?
Now, this is an expression of that charge is conserved. You have this equation when charge is conserved. And now, if you look at this equation, you can write this as dx, sorry, dj k dx k plus d dx0 of rho, and x0 is c times t. And this is equal to 0. I can write it as this way. And I also can write it then as d dx mu, where now mu runs from 0 to 3, of a new vector that is j mu, and j mu is rho comma j, and the mu component of this. And this is the forward current. And we know, and this is equal to 0, because this is equal to 0. We know that this is a forward vector, and because the indices are in the right place, this must be a forward vector. So we know that this is the correct forward vector for electrical current and charge.
I can see that.
And you know that the two are related, because it might, if you have a wire like that, and there's a current, and you also have isolated charges, they may look quite different. But if you have a charge and the charge is moving, it actually becomes a current. But there's relativity. Instead of a charge moving, I can walk away from the charge, and that this charge is also moving. So the two are actually two of the same things. And that is why in relativity, the two are combined into one vector.
I see. So I don't know if I'm misunderstanding this, but I can't really visualize the forward current that well. So if I had just, I don't know, this might be a dumb question, but if I had this as like 1, 2, 3 or something, how could I express the forward current? Or
yeah, no. So you say J is J1, J2, J3. That's a three-dimensional vector. Then J mu is the charge density times J1, J2, and J3.
Oh, okay.
And these are all functions of space-time. They're all functions. Functions of four variables of time and space. So this is x mu, so to say. It's a different, second called x alpha. It's a different mu than this. And here there's a mu index.
Okay.
To visualize them, you could ask what J means. So it's the current density.
Is it just the direction? The charge is flowing overall?
It is Q times V. So this is like a moving charge, because this is velocity and that is Q. And we also have that J times the area, that is equal to the current. So there's a current density and there's a current. So if you have, say here that there's a current flowing in, so the current is here. So the current that's flowing in is J times this area. That's the current. And the current I is by definition the charge dq dt.
Okay.
And if the charge moves with velocity v in 1 second, if we take dt 1 second, and this moves with v in 1 second, then the charge that flows in is this is the current density. It is equal to J times V times the area, because that is we have that J times the area is the current, and in 1 second this moves by a velocity v. So that means the total, you get the total charge that flows in is the charge in the volume. In 1 second it moves like this, because that is what V is.
So with the definition of the forecurrent, how would we proceed towards defining the potential?
Yeah. So then we have to go back to the Maxwell equations. And the Maxwell equations, they can be written in the following form. That and I need a cheat sheet for that. And in my lectures, I did not derive that. That is equal to minus 4 pi times the charge density. And this is the potential. And del squared minus 1 over c squared dt squared acting on A is equal to minus 4 pi over c times j.
Right. So, is this notation for that, or?
Yeah. Okay. This is the square of the derivative. So it is really notation of this. It is dd x squared plus d y squared plus d z squared.
I see.
And
what does partial t? Could you expand partial t? Or, could you expand partial t? What does it represent?
You mean this?
This.
No, it is a time derivative.
Oh, okay.
It's the time derivative, the square of the time derivative. And
so, all right. So that means that the divergence of the gradient of A minus 1 over c squared times the time derivative like this, or?
No, it is second derivative.
Okay.
That this is the second derivative of a, d squared a dt squared.
Right.
Just a second derivative.
This would be a partial derivative, right?
Yeah, you don't you only differentiate with respect to t, and not so this is a function of x and t. It could be that x also depends on time, but that then you don't you only differentiate the explicit time dependence.
Okay.
And here there should be a factor c, and here there should be a factor c. So the 4 factor is actually with the c included. So the continuity equation doesn't have the c. When I did this, okay, I everywhere put, there should be no c here. So if you look at these equations,
it might be because that -1/c constant was washed out somewhere.
No, I shouldn't have, because I wanted to make a relativistic invariant combination, and I forgot to multiply this by c. So now you see, if I multiply this now by c and divide by c, then we get exactly the combinations c rho and j. And here we get phi and a. So that means these two equations we can summarize as, in one equation, and I wrote the 1/c squared, acting on a mu is equal to 4 pi, in fact minus 4 pi over c times j mu. And for mu equal to 0, you get this equation, and for mu equal to a spatial component, you get this equation. And that means these two equations, these two Maxwell's equations, actually one equation. And these equations you get from the Maxwell's equation by substituting that the expressions for E and B. E is equal to the gradient minus the gradient of phi plus 1/c dA dt, if I do it correctly. So you can express the Maxwell equations in terms of the potentials. And if you do it correctly, you get these results. And these are important equations.
Right, so we already have a definition for the 4 current, and now we've expressed the 4 potential in terms of the 4 current.
Yeah. We know that this is a 4 vector. We know that this is relativistically invariant. And that means that this must be a 4 vector. So A mu is a 4 vector. So we know how electric and magnetic fields transform on the Lorentz transformations. So A mu transforms on the Lorentz transformations exactly the same as X mu. And if we know A mu, we can calculate the electric and magnetic fields, so we know how the electric and magnetic fields transform on the Lorentz transformations.
All right, so we have proof that it's invariant, but are we supposed to isolate it, or can we isolate it?
Isolate what?
The 4 potential on this side. Can we express it solely in terms of J mu?
Express it in terms of?
No, never mind.
Oh yeah, you can solve it.
Yeah.
So A
solving
mu
for A mu.
is del squared minus 1 over c squared ddt squared to the power minus 1 acting on minus 4 over c times j mu. So that's solution.
I'm not sure exactly how you would power this to the minus 1. Yeah. I think we're getting into magic more than math here.
Yeah, this is actually an operator, so you have to invert an operator. And this is called, this thing is called a Green's function.
So there's no way to express it in terms of gradient or divergence or curl or
No,
anything
no,
like
no,
that.
no. You can you can work this out. You can calculate what it is, and you actually can solve for it.